All right, we're going to continue exploring the concept of equilibrium constants and chemical equilibrium and figure out what else we can learn. So learning objectives for this segment are, as I share the screen, the learning objectives are going to be able to calculate equilibrium constants from partial pressures and vice versa, be able to relate equilibrium constants Kp and Kc, we'll talk about what Kp means, and write equilibrium constants in equations with multiple chemical equations with multiple phases. There's some tricks there that actually make things pretty easy, but have to be kept in mind. Okay. So equilibrium constants for gases in terms of pressure. It turns out that you can write equilibrium constants for gas in terms of pressure as well. Frequently with gases, we keep track of equilibrium in terms of partial pressures of the gases, and we call this Kp. The equilibrium constant K written in terms of the pressure P. Let's apply this. 150 liter vessel contains an equilibrium mixture of 0.1 molar NO, 0.15 mole of bromine, and 0.250 moles of NOBr at 25 degrees C. What are the values of Kc and Kp for this reaction? Well, we can calculate the concentrations relative. Let's write the equilibrium constant in terms of Kc. So Kc, right, and there's our reaction. So Kc is going to be NOBr, and in the reaction there's 2, so squared divided by concentration of nitrous oxide, bromine 2 Br2, no, not squared, just Br2. There we go. All right, so we can calculate, we can read right off essentially the concentration of NO because it's 0.1 mole over 1.5 liters, so that's 0.66, nope, not that much, 0.0667 molar. Concentration of bromine is 0.15 molar divided by 1.5 liters, 0.1 molar, and the concentration of NOBr is 0.25 moles over 1.5 liters, and this gives us 0.167 molar. So our Kc is just going to be 0.1667, and that's 667. Again, now the molars disappear because once they're in molar, we divide by 1 molar. To get rid of the unit, 0.0667 times 0.1, and that gives us a 62.4, a Kc of 62.4. So what would the Kp be in terms of partial pressures, right? If we have the pressures of each of the equilibrium, each of the reactants, that'll be in partial pressures. So this would be partial pressure of NOBr squared. Everything is this, we just plug partial pressures directly in place of equilibrium constants. Partial pressure there. So what are the partial pressures of each of them? Well, the overall pressure, nRT over V, which is going to be 0.5 moles total, right? There's 0.1 plus 0.15 plus 0.25 equals 0.5. 0.5 moles, 0.08206 liter atmospheres over mole Kelvin times 298 Kelvin, all divided by 1.5 liters. Liters cancel, moles cancel, Kelvin cancel, it leaves atmospheres. If you plug that in, you get 8.16 atmospheres. And so the partial pressure of NOBr is going to be 0.25 moles over 0.5 moles, that's the total number of moles, times 8.16 atmospheres, that will be 4.08 atmospheres. Partial pressure of NO is going to be 0.1 mole, 0.5 mole, 8.16 atmospheres. That gives 1.63 atmospheres. and partial pressure of bromine is going to be 0.15 moles over 0.5 moles times 8.16 atmospheres, which gives 2.45 atmospheres. So we plug it in, the Kp is going to be 4.08 squared over 1.63 squared 2.45. And that, oh, I forgot a square over here. There we go. That gives us 2.56. All right, so we have a Kc of 62.4 and a Kp of 2.56. These have the same physical information in both of these. Both of these describe the same equilibrium, right? We did them with the same amounts. All we did was do it in different units. So these are just two different ways of keeping track of the equilibrium. And you'll see both of them in experimental data or chemical textbooks. So it's important to know how to work with both of these. If you're dealing with gases, frequently it's easier to measure the pressure. So maybe with an entirely gas phase reaction, you'll see most of these in partial pressures. If you have a reaction that's in aqueous solution, obviously concentrations make much more sense. They're not gases. And so you'll have Kcs instead of Kps. And just a way of thinking about the fact that they have the same content of information, you can actually relate these two. Let's look at the relationship. Let's assume that we're in the ideal gas limit. If you're not in the ideal gas limit, it becomes a little more complicated because the connection is a little more, you have to do some more math there. But let's assume that the ideal gas law holds. So, PV equals nRT is the ideal gas law. Divide both sides by volume. You have N over V, but N over V, right? That's just the concentration. So the partial pressure of A is going to be the concentration of A times RT, right? And so we can replace concentrations with pressures or pressures with concentrations. If the ideal gas law doesn't quite hold, you'll have to do a little bit more math there to relate between the two. So that means we can convert from Kc to Kp using just this expression. Kp is equal to Kc divided by RT over delta N. Let's just do that with something really simple. I'll show that, so where N equals the moles of gas products minus the moles of gas reactants from the stoichiometry of the equation. Let's prove this. So let's take a really simple problem. Let's just say we're looking at, we have Kp of a simple reaction where it's just A squared over B, right? Okay, so I should write that in terms of partial pressures so it's super clear. So here we have a partial pressure of A. So our reaction is, let's do it, A goes to 2B. Let's just do that. Okay, so then for this reaction, we'll have concentration of B. For this reaction, we'll have partial pressure of B squared, this is Kp, over partial pressure of A. But from up here, we know that this is a concentration of B times RT squared, and this is going to be concentration of A to the RT, and this is going to be Kc times RT squared over RT equals Kc times RT. And so you can generalize this depending on exactly how many moles of gas there are in the product, in the products versus the reactants, right? So you can plug this in general. You're always going to get some relationship. Kp equals Kc times RT to the power of the number of moles of gas. So let's say this is both a gas phase reaction. And so we start with 1 mole of gas, ended up with 2 moles of gas. You can see here this RT is to the 1 because delta, the change in number of moles of gas is 1. It goes from 1 to 2, so the change is 1. So let's look at the last slide, right? In the last slide, then we had, going back, let's go back one slide. So there we started off with 2 moles of gas plus 1. And so we had 3 and we went to 2. All right, so here then we have delta N was 2 minus 3 equals minus 1. And RT equals 0.08206 liter atmospheres over mole Kelvin times the temperature, which is 298 Kelvin. And these cancel. And so we get, this is 24.45. And it's just a pure number because everything is, the partial pressures, their standard state is 1 atmosphere. So you divide by 1 atmosphere there. Again, there's no numbers there either. But here the conversion factor is 24.45, no units. And so we would get the Kc should be RT to the minus 1, because that's what the change in moles of gas is, which would be, from the last slide, 62.4 times 24.45 to the minus 1 equals 2.55, which is Kp, right? That's exactly what we had. I guess we had 2.56, but there's obviously some rounding going on here. It's only accurate up to 3 digits. So we only have 3 significant digits. So that shows how these two things are equal. They contain the same physical information. You just use whichever one is more convenient to work with.